3.2 is logarithmic functions. So today we're going to start talking about logs, and then we're going to move into graphing and then solving log equations. And there is a relationship between logarithmic functions and exponents. They're actually inverses of each other, and we'll talk about that in a minute. Before we do that, though, a couple of things that you must understand that you learned in Algebra 2 that we're going to quickly recall. Going from radical notation to rational, an exponent. If you have a base right here underneath, the base is going to remain the base. But what can happen here is we can write something that has a radical, something in radical form, as a rational exponent. And whatever your power is right here is going to stay on the top. Whatever your nth root is going to go on the bottom. So this right here can also be written as a rational exponent right here. You can also go the opposite way and go from rational exponent to radical notation, which isn't very common. So take a look at these. We can, instead of writing this as the square root of 24, we could say, well, I know this is a square root, so really there's a 2 there, and I know 24 is really to the first power, so I could write this as 24 and keep the power with it. The power goes on the top, and the root goes on the bottom, so I could write this as 24 to the 1/2 power. We talked about this early in the year. The next one I could write has a power of 1, 2 to the 1/3 power. The last one I could write as a to the 2/5 power. Now that's going to be important for what we're doing in a minute. That's why we're reviewing it. So 3 rules of exponents that you must know for this unit. If we have a to the m over n power, that is the same as the nth root and a to the m power. If we have something to the 0 power, anything to the 0 power is always equal to 1. Doesn't matter what that is. If we have a negative exponent has to be positive. In order to make it positive, you put it in the denominator. So this is going to move down to the bottom. It'll then become a positive exponent. So these are our 3 rules of exponents that we're going to be using throughout this unit that you must recall and know how to use. So moving on to logs now. The definition of a logarithmic function. A logarithmic function can be written as a base with a power. Here's the definition right here. The log with base b, this right here, that small number is the base. And so log of x with base b is how we would say that is equal to y. That is the same as saying b to the y power is equal to x. Now I'm going to use terminology here. When we have something that goes to a power, this is the base. So notice this. The base b on the right is going to a y power. The base b on the left is that small number that is the base of a logarithmic function. Here are a couple examples. We have log of 100 with base 10 is equal to 2. What that means if we rearranged it, because logs don't make sense in our mind, but exponents do. That means 10 to the second power is equal to 100. And we can look at that and say, yep, indeed, 10 squared is equal to 100. The next one, if you look at log of 8 with base 2 is equal to 3. Makes no sense in our mind, but if we rearrange that using our definition of a log, it says 2 to the 3rd power is equal to 8, and that does make sense. And 2 times 2 times 2 is definitely equal to 8. So what we're going to do today is we're going to convert from logarithmic form into exponential form and exponential form to logarithmic form. In order to do that, you must understand what it means to have an inverse, because these are inverses of each other. A logarithmic function and an exponential function are inverses. What it means to find an inverse, you did it in Algebra 2, is you switch the x and the y, and then you solve the equation for y. So for example, if we were asked to find the inverse of this, we would switch the x's and the y's like this. And that's how we get to this. Now, technically, you should solve that for y, but clearly we don't know how to do that yet. We are going to eventually get there. But inverses are switching the x's and the y's. If you look at these two graphs, the blue and the red, they're inverses of each other. And if you look at the tables, you'll be able to clearly more identify why they're inverses. If you look at the first ordered pair, -2 and 1/4, -2 and 1/4 is that first point there. If I switch the x and the y, then this will become the y will become the x will become the y, and look what I get. I get 1/4 -2. Well, 1/4 -2 is this point. I could continuously take a look at all of these. Let's look at the last one. I have 3, 8 for that. So here's 3, 8. If I switch the x and the y, I get the last point here, 8, 3, and you can see 8, 3. So that's why these are inverses of each other. This first one right here was the exponential function y equals 2 to the x power, or f of x equals 2 to the x power. The inverse is the log function, rearranging it, g of x equals log of x with base 2. So let's talk about how we can change from logarithmic form into that more familiar exponential form. If you switch from log to exponential form, you always start with the base here, this small base value. And what you do is this base is going to go to this power. So the base right here, okay, the bases, b's are both bases. The base becomes the base of an exponential power. It comes to the y power, and then it comes back and it equals, we cross the equals, and it equals what we're taking the log of. So b to the y equals x. Here, coming around to this power, and it's equal to x. That's the pattern. And we'll practice with a couple of examples. Taking a look at this, it says change from log form to exponential form. We need to get rid of the logs. In order to get rid of the log, you always start with the base here. The base goes to this power, so 2 to the 3rd power. Coming around, we pass the equal sign, and that's what this is going to equal, and it's going to equal 8. 2 to the 3rd is equal to 8, which is a true statement. The next one, 8 to the 0 power is equal to 1. 8 to the 0 power is equal to 1. Sort of looks like a little heart right there that's created. Anything to the 0 power is equal to 1, so we know that's true. Now, looking at the next one. Again, we start with the base here of the logarithmic function, coming around to what it's equal to. 3 to the -2nd. What is that equal to? It's equal to 1/9. Indeed, 3 to the -2nd is, because remember we would need that to be positive, so we would put it in the bottom. So we'd have 1 over 3 to the positive 2nd power, which is equal to 1/9. The last one, we're going to start with the base here, coming around to this power, so 2 to the -4th power. It's equal to 1 over 16. Again, to make a negative exponent positive, we just put it in the denominator. So this is the same as 1 over 2 to the +4 power. 2 times 2 times 2 times 2 is 16. So that does indeed give us the answer right there. Now we're going to work it backwards. So we're going to change from exponential form into logarithmic form. And the pattern's the same. It's just reversing it. And here's how I like to remember it. The base remains the base. The other two switch places. So what does that mean exactly? Well, we need to know what the bases are, obviously. The base of an exponent is the big number. The base on the logarithmic function is that small number right there. So you will notice the base here remains the base there. The other two switch places. So we had the y coming first, now the y is second. And the y was last, and now it's in the middle. So the base remains the base, the other two switch places. Whatever the base of the exponent is becomes the base of the log. We'll switch the other two around, keeping the equal sign where it is at. Now let's do a few problems. Now all these are true statements. We know 25 to the 1/2 power is equal to 5 because 25 to the 1/2 power is the same as the square root of 25. And we could check all of these. But that's not what we're asked to do. Actually, I have the directions wrong in here. it says change from this should be exponential form into logarithmic form. Okay, so the base remains the base. The base to this is the big number right here. That's going to become the small number, the base on the logarithmic function. The other two switch places. So we have to have a number here, equal sign, and a number there. Well, the 5 was last. The 5 now is going to go before the final number. The final number was the one that was in the middle before, so we just switch places. With the next one, again, you write the word log, determine what the base is here. It is a 2. That's going to become the base on the log. The other two switch places. So we need something here and something here. Whatever was last is now going to go in the middle. Whatever was in the middle is now going to go last. And you can pause the video and try the other two. And those are what your answers should be. Now, the majority of your problems that you're going to work on today on your worksheet are going to look like this, and it says evaluated without a calculator. Now, you have no idea what this is, and you won't have any idea until you first write it in exponential form, so it makes more sense in your mind. You want to get rid of the log. So remember, what you do is you take the base. It's coming around to this power. It's going to be equal to this. I don't have anything there. Of course, if I don't have anything there, I can create a variable. So that's what I'm going to do. So this is 3 to the x power equals 81. Now this makes sense. Now I just need to know what number goes in there to make this true. Well, I know 3 squared is 9. So 3 to the third, yep, that's 81 right there. So x is equal to 3, or this answer right here is equal to 3. I guess technically I don't have to put x because I put that in. Now the next one, same thing. 36 to this power has to equal 6. 36 to the x power has to equal 6. Now here's an example in which I have a base that is going from a bigger number to a smaller number when I go to an exponent. So one of two things is happening. Either I have to have a fraction or I have to have a negative exponent. Okay, it's not just going to be 1, 2, 3 because obviously my number is going to get bigger when I take 36 to that power. Well, I know a negative exponent creates a fraction. Okay, so if a negative exponent creates a fraction and I don't have a fraction here, that's probably not what I'm looking for. Instead, what I probably am looking for is a fraction, because remember, a fraction ends up being a radical. So I can take and I can just start plugging in numbers. Well, first of all, hopefully you see the relationship between 36 and 6 is it's the square root. The square root of something is, remember, if we write that, it goes to the 1/2 power. So x is actually going to be equal to 1/2 on this. 36 to the 1/2 power is equal to 6. Now, if you didn't know that, if you can get the idea that it's a fraction, you would just start guessing. So you would take 36 to the 1/2, 36 to the 1/3, 36 to the 1/4, to the 1/5, and so on until you get it. So it's just kind of a guess and check in your calculator if you don't have that number sense. And the last one here is this 5 to the x power is equal to 1. And I need something equal to that's giving me a 1. I could try those fractions. It's never going to work because taking the square root, third root, fourth root, anything of 5 is going to give me an irrational number. Negative exponent brings a fraction. That's not what I have. And what this is this is x equals 0. Remember, anything to the 0 power gets me back to 1. Here are 3 problems in which you can try. So I would ask you to stop the video and give them a try and then bring it back and check your answers. All right, these are the answers you should have. The trickiest one is number 5. And reason being is because you're starting with a big number and you're getting to a fraction. Immediately, a number to a fraction means you have to have a negative. But in addition to that, you're also starting with a big number, 9, and getting to a smaller number, which is 3, which means you have to also have a fraction. So now you have a negative fraction, which is a negative 1/2. Number 6 should be pretty easy once you rewrite it, because you're going to notice that because the bases are the same, 2 and 2, the powers also have to be the same to make this true, so x has to be equal to negative 3. And just a couple of the other things that I want to run through. I want you to be able to visually see these. If you ever have a base being the same as the big number right here, what the answer is going to be whatever the exponent is equal to. So the log of 7 with base 7, if you're taking the log of a number and the base is the same, it essentially simplifies away and gets rid of that log. And what you're left with is 2. Likewise, going in reverse, if the base is the same as a log with the base, so base 5 and log base 5, then the answer is what's left right here. Now you could actually plug this into your calculator. No, you can't either because you don't know how to do the change of base on that. The next one is similar to A. The bases and the big number are the same. They simplify away and leave you with that exponent, which we know is a 1. And the last one, anytime you're getting to a 1 right here, your answer is automatically going to be 0. And that just is, if we rewrote that, 6 to the x equals 1, now you can clearly see it. But just kind of a hint, anytime you're taking a log of 1, it doesn't matter what the base is, the answer is 0. And with that being said, you are going to work on assignment 3.2 and go ahead and submit that into Schoology when you're done. Make sure when you are working on the backside that you are showing me your setup. So before you tell me the answer, you're going to tell me like 3 to the x is equal to 1/3. You're going to write your setup like this before you tell me that your answer is -1. And submit it to Schoology when you're done. Have a great day. Bye.